All right, gang, we've got just 2 more lessons to go to finish up this year, and so sorry we weren't able to get to this one in class today, but hopefully this will give you an idea of what the fundamental counting principle is all about. I was kind of just thinking about our seniors and all the choices that they've had to make, decisions they've had to make over the last couple months, and out of curiosity I did a quick Google search to find out how many colleges we have in the U.S. Colleges and universities, ones that you could get a 4-year degree at. So I'm not counting community colleges right now. I was just looking for this. So Google told me that in the U.S. that there were, whoops, I got the numbers mixed up, 3,864 accredited colleges and universities in the United States. Now, again, those are accredited, not like online, but like actual colleges and universities. Then I got to thinking about how many majors there are out there, and that number varied from school to school. So some schools only have a few majors and some have a ton. So we're going to go the conservative estimate and say that there's about 170 different majors you could have out there. So any given senior has to choose both their college and then eventually choose their major. And so the number of choices that a senior has are the product of those two things together. So 3,864 multiplied by 170, which turns out to be 656,880. That's how many different options there are when you multiply those two numbers together that the seniors have to choose from. Okay, choose your college first and then choose your major, and you could do that 656,880 times. That's an example of the counting principle, the fundamental counting principle. If you want to count the number of options that you have available to you, you multiply the number of choices that you have. So let's try and take a little bit of a less stressful example, and let's just think about ordering lunch. So let's imagine that you're going up to the counter at In-N-Out and you have to make a decision. All right, so how many choices are there? How many different ways could you order that burger based on the options that In-N-Out has? And so you have to decide how much meat you want. You have to decide if you want cheese or not, and toppings like onions and tomatoes, lettuce, pickles, spread. Boy, it just can go on and on. Spread, pickles. All right, so if you had to consider, you got to make all those decisions when you're standing there at the window. Right, so how many meat options do you have? Well, typically at In-N-Out, there's just 2. You can either have 1 or 2 patties. So we'll say you've got 2 choices for that. For your cheese, again, you technically have 2 choices. I know they don't have 2 kinds of cheese, but you have 2 choices. You either have cheese or not, and that's 2 choices to say yes or no. Onion, you've got 3 options when it comes to onion. You could have no onions, you could have grilled onions, or you could have fresh onions. So that's actually 3 different choices. Tomato, 2 choices, because yes, I'll have tomato, or no, I won't have tomato. That's 2 different decisions you could make. Lettuce, same thing. Spread, same thing. Pickles, same thing. So if you take all of your different choices and multiply them together according to the fundamental theorem, or the fundamental counting principle, 192 different ways you could make a burger. That's called the fundamental theorem. Okay, the fundamental counting principle. You have that many different types of burgers that worker could make. And then there's other that we haven't even talked about, like ketchup and mustard and putting other things on. This is just the basic things you order. This is an example of fundamental counting principle. So another way that is put into play is when you get a license plate for your vehicle. In California, a license is 7 digits long. And so let's kind of imagine that we've got 7 blanks to fill on this license plate. 1, 2, 3, 4, 5, 6, 7. Now, there could be custom license plate, but your standard normal license plate in California starts with a number. So it's going to be a number here. That's not a hashtag, it's the number symbol. And then a letter. and then another letter, and another letter, and then 3 more numbers. Okay, so let's imagine that we're creating a license plate. So how many numbers are there to choose from? Some people say 9 right away. You've got 9 different numbers you could fill in, but they're forgetting that you could use 0 also. So 0 is the 10th, so there are 10 different things that could go in that first position. For the alphabet, there are 26 letters in the alphabet, and you could use the same letter again, over and over again. So each time you could choose from 26 different letters. And then your numbers are still 10 again. And so if you take all of those license plate products and you put them all together and you multiply according to the fundamental theorem, you end up with, how many different license plates can we have? 1, 7, 5, 7, 6, 0, 0, 0, 0. So that is 175,760,000 different license plates that could exist in that configuration. Now, if you started making some other rules about license plates, different states have different rules. Maybe you want to say that you could never repeat the same letter or number. Well, then how would that change the result according to the fundamental counting principle? Well, at the beginning I have 10 numbers to choose from and 26 letters. But the next time I choose a letter, I can't choose the same one that I already used, and so that's 1 less, so that would be 25. And the next letter would have to be 24 because it's 1 less than what I chose the time before that as well. Same with the numbers. If I've already chosen a number out of the 10 I have to choose from, well, that's going to decrease to 9, and then 8, and then 7. So that would be a rule saying, okay, you can't repeat anything. So that's going to change the number of options if that was a rule. So we'd expect that number to go down, and it does. 786240000. So now we only have 78 million by making the rule that you can't repeat a digit that you've already had. Okay, designing a phone number would be similar. How many different phone numbers exist out there? Well, a phone number has a total of how many digits? Let's think about it. Okay, so your phone number is going to have 3 digits for the area code, and then it's going to have 3 digits for your prefix, and then 4 digits that come after that. Okay, so that's how long a typical phone number is. So that's a total of 10 numbers, 10 blanks to fill in. Now we know that phone numbers can't start with 0, and so there's only 9, in fact, and also actually, you can't even start with a 1 either, because then they think 0, you'd think international, 1, you'd think long distance. So a phone number cannot start with a 0 or a 1 with its prefix. So that means we only have 8 numbers. We can choose 2, 3, 4, 5, 6, 7, 8, 9. That's 8 different numbers to choose from, but not 0 or 1. The rest of them can be 0s and 1s, and so the rest of them could be 10 all the way down. So how many different options is that? Well, a better way to write that might be 8 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9 times. That would be 8 with 9 zeros coming after it. So that's 8 billion different phone numbers that could possibly exist. I'm sure eventually we'll run out and we'll have to make our phone numbers even longer. That's what's always happened. When they first started with phone numbers, they were only 3 numbers long, or then they ran out of numbers, and they went to 4 numbers, and they ran out of numbers, so they went to 5 numbers, and it just keeps getting bigger and bigger as we run out of numbers. So eventually we'll use up all of the 8 billion phone numbers that exist, and we'll have to make our phone numbers even longer still. How about taking a quiz? Let's imagine that you are taking a quiz that is a combination of true-false and multiple choice. And the quiz is going to be 8 questions long. And if you're just totally guessing on this quiz, how would you do? 1, 2, 3, 4, 5, 6, 7, 8. I guess that's 1 too many. All right. So let's say that the quiz splits right here. In the front half of the quiz, that's going to be our true-false section, and the back half of the quiz, that's going to be our multiple choice section. So if you're just totally guessing, well, the true-false section, you have 2 choices, and then the next question is 2 choices, and the next question, and the next question. So you have 4 true-false questions right in a row. Then you get to multiple choice. And let's say that there are 5 options, A, B, C, D, E. And so you're going to have 5 things to choose from every time. Do I choose A, B, C, D, or E? And then the next time, and the next time. And so we want to, that would be 2 to the 4th, and 5 to the 4th. Okay, and that's going to come up with 10,000. So there are 10,000 different possibilities of right answers on a little 8-question quiz. It barely seems like it's even worth it, and yet 10,000. And so your chances of blindly guessing and happen to getting them all right are going to be 1 out of 10,000. So not super good odds. Let's suppose that we are filling a committee, and there are, say, 24 students, and we're picking 5 of them to be on a committee randomly. Okay, well, so I have to make 5 decisions. Decision 1, 2, 3, 4, 5. So I look around the room, and there are 24 people to choose from, so I'm going to, got 24. Well, I pick my first one. That leaves me with 23 students. That leaves me with 22, 21, and 20. So how many different combinations of these student groups could I pick in order to, form this committee? Well, I get 5100480. So it's 5,100,480 different ways I could form a committee using different people from the group. It has to do with like the way I make a seating chart too. If I look at the 19 of you in class and I want to make a seating chart, well, the first person I pick, I have 19 of you to pick from, and then it descends each time till you guys are all in a different seat. It also works with scrambling words. So let's take the word golf. There's only 4 letters. How many different ways can I rearrange those 4 letters? Okay, well, I could make you list them all for me. So, I could do O-L-G-F. I could do F-L-O-G. Okay, which is what you feel like doing to yourself right now. Okay, I could just mix all of these different, but how many different ways if I wanted, without writing them all down? Okay, well, the first space could be filled with 4 letters. The next space, there are 3 letters left, and then 2, and then 1. Now this is an example, 4, 3, 2, 1, of a special kind of multiplication called factorial, and we write it like this. Okay, so if it was 4, 4, 4, 4, we would write that as 4 to the 4th. That's what powers are. Okay, but that's not what we're talking about. We're talking about 4, 3, 2, 1. That is called factorial. So when anybody writes a factorial symbol, that means you're supposed to start with the number 4 and then multiply 4, 3, 2, 1, which actually turns out to be the answer of 24. Factorials are a nice handy thing to save you time in multiplication or save you time in writing it all down. That would be 4 factorial. There is a factorial button on your calculator. If you hit the math button, and over on the far right hand side is a column called PRB. It stands for probability, and under that column you would see exclamation point, which is what factorial is. So let's see how this works with other words. So let's take the word valley, for example. All right, well, there are 6 letters there. So 1, 2, 3, 4, 5, 6. So is it just as easy as 6, 5, 4, 3, 2, 1? Is it just 6 factorial, the same as it was with golf? And the answer is no, not quite, because the word valley has a double letter in it. Okay, the L is duplicated. And so that duplication throws you off a little bit. And so yes, you do 6, 5, 4, 3, 2, 1 to represent the 6 different letters, but you have to also divide that whole problem by 2 factorial because there was a duplicate letter. And so it would be 6 factorial divided by 2 factorial. And so if we work out 6 factorial on our calculators, or if you work it out by hand, 6, 5, 4, 3, 2, 1, 6 factorial is 720. 2 factorial is 2, and so the answer is 360. So there are 360 different scramble combinations on the word valley. If we did the word Cerritos, C-E-R-R-I-T-O-S, how many different word scrambles can we make on that? Well, Cerritos is 1, 2, 3, 4, 5, 6, 7, 8 letters long, but it also has a double letter of the double R. And so that would count for the double letter. And so we would have 8 factorial, which is 40,320 divided by 2. So you're looking at 20,160 different ways that you could mix up the letters of Cerritos. Now some of the words are going to be nonsense words. They won't all make this sense, but there's still a different rearrangement of those letters. The last one I wanted to look at is the word banana. One, 2, 3, 4, 5, 6. All right, 6 different letters, but we've got several duplicates here. There are duplicate N's, so that would be a 2 factorial, and there are triplicate A's, so that would be a 3 factorial. So that's going to seriously lower the number of rearrangements of this word that I could have. So we know that 6 factorial, we've already taken a look at that, that's 720. 2 factorial is 2. 3 factorial is 6. So this is 720 divided by 12. And so that's 60. And so there are only 60 different rearrangements of the letters in banana compared to how many there were in a 6-letter word like valley. So the fundamental counting principle can help you count options when it comes to how many choices you have. It also can help you count options when it comes to word scrambles. And then tomorrow we'll look at probability and how these different options affect the likelihood of you getting what you want. All right, have a good night. I will see you guys on Thursday.